Hi, in this lecture we are going to discuss causal graphical models. So up to this point we have mainly used graphical models to represent probabilistic distributions and to answer probabilistic queries. In other words, we asked questions such as what is the probability of one variable given evidence about another variable? However, in many real-world problems, we want to ask a bit of a stronger question. We don't only want to ask whether variables are associated, we also want to ask whether one variable causes another variable. That is, the event in a particular variable is caused by an event in another variable which is linked to that variable. So in this lecture, we're going to introduce the difference between probabilistic reasoning and causal reasoning, and we're going to explain why standard probabilistic graphical models, such as Bayesian networks, are not enough for causal interpretation and causal questions. So we'll have to extend that kind of framework that we've been busy with all the time to be able to answer causal queries, and this is where we get this idea for causal graphical models. So it's based on the same framework, it's just that we're expanding this framework for causal interpretation. All right, so let's look at the problem statement as we always do. The key problem here is that if we only care about standard probabilistic queries, then causal structure often doesn't matter. So as long as the model correctly represents the joint distribution, then we can answer queries such as the probability of y given x. But causal questions are quite different. This is also a very difficult area in machine learning. It's arguably the most difficult when you're trying to learn causation in observational data. In sociology, it's very easy. There you can just split up the control and the experiment, and you can do some kind of intervention on one group and then compare the difference with that group to the other group where you didn't do the intervention. And then you can see if the intervention caused a particular behavior to happen. Right, but in observational data, this is very difficult. So learning causal associations from observational data is an NP-hard problem. It's often not even identifiable. It's the most, from every perspective, it's the most difficult problem in machine learning. However, so I was saying that we often want to answer causal queries, such as in a Bayesian network, the probability of one event given another. But I was also saying that causal questions are different, right? So that asks specifically, what would happen if we actively change something in the system? So for example, we might ask whether preventing smoking would reduce lung cancer, or whether a student would have passed the PGM exam if they skipped all the lectures. A normal Bayesian network can represent dependencies between variables, but they can't necessarily represent an actual causal mechanism. That means they can't always tell us what happens under the intervention. So an interesting way of thinking about this is that the probability is often about prediction, and causality is often about control. So that's how most people think about it. So the probability is about prediction, and causality is more about controlling a specific variable. So if I only wanted to predict whether someone will get lung cancer, then correlations may be useful. So smoking, age, occupation, family history, and many other variables may help us make a prediction. But if I want to decide what action to take, then prediction is not really enough. I need to know what will happen if I change something. For example, if I prevent smoking, right, will the rate of lung cancer actually decrease? And on the other hand, if I force someone to smoke, will the rate of lung cancer increase, or if we force populations to smoke? So this is why causality, it matters so much in medicine and economics and policy, and in AI as well, robot moving around an environment, because many real decisions are not only prediction problems, they are also intervention problems. So we need to know how to do things in that particular scenario. All right, so this is where the distinction between conditioning and intervention becomes important, right? So conditioning means that we observe a variable. For example, we observe that the student attended lectures. Intervention means that we force a variable to take a particular value. So for example, we force the student to attend lectures, or we force the patient to take the medication. We write interventions using the do operator. So you can see, do z is equal to small z, where the big Z is the variable and the small z is the value of that variable, a particular value. So it means that we're deliberately setting the variable z to the value small z. A typical causal query therefore has the form the probability of y, and we do a particular thing, which is setting the small value, and then maybe some evidence, maybe other things we know about the context. This asks, for example, what is the probability of y given that we intervened to set the value of big Z to be small z, of particular value of that variable. So these are not the same thing, right? This particular you can't really call it evidence. This is forcing the value z to take the small value z, and this is just given some evidence. These two things are not the same thing, right? So observation gives us information about the world, and so gives us information about the context, but the intervention changes the world. This specifically is something that we might have never seen in the training data. It's changing exactly. It's changing everything. It's changing even the structure of the network. Okay, so let's look at a medical example, because this is often where we want to use stuff like this. So consider this medical example. The question is, if we get a patient to take this medication, what are her chances of getting well? So this is not just simply the probability of M, the probability of a particular health given some medication, right? It's not just that. So it's quite different. So this here is the probability of health given that we observe the patient taking the medication. So instead, the causal question is this one over here. So this means, what is the probability of health if we intervene and make the patient take the medication? This is a very different kind of scenario. So these two quantities can be different, actually. So patients who take medication on their own may already be more health conscious, may follow medical advice, so this is the scenario, more carefully, or may have better access to health care. So their improved health may not necessarily be caused by the medication alone, okay? The do query here, this one here, it tries to isolate the specific causal effect of the medication itself. So this is very different from, these are very different kinds of inference queries. Now this is why randomized controlled trials are so powerful. If a patient chooses on their own whether to take the medication, then the treatment group may differ from the non-treatment group in many ways. They may be wealthier, more health conscious, like I said, less seriously ill, or may be more willing to follow medical advice. But in a randomized trial, we try to make the treatment assignment independent. And we'll see more of this later on when we talk about these causal, what are they called, twin counterfactual models. So we try to make the treatment assignment independent of those background factors that I mentioned. In causal terms, we are trying to make the treatment behave more like an intervention and less than an observation. So this is why the do operator has its own notation. It's specific notation to show the case where we are forcing the medication variable to take a particular value. So it really captures the logic behind the experimental design. But not only that, right? Because you'll find that answering this query here, even using probabilistic inference, is very different from answering this query here. Here there are structural changes that need to be made to the network itself so that we can answer this query compared to this one over here. And that structural changes gives us this way of capturing the logic behind the whole do. It's the part of do calculus. The logic behind forcing a value to take a variable to take a particular value. All right, I hope all of this is making sense. I know it's quite technical, but it's pretty important. So here's more examples, right? It's always good to have more examples. So here we have several examples of intervention queries, right? So this is different from probabilistic queries that we looked at before. So the first one, if we lower the price of hamburgers, will people buy more ketchup? Can you see the difference, right? It's will people buy it, not do we observe people buying more ketchup. If we lower the interest rate, will inflation increase? If students study PGMs every night, will they get an A for the course? This is very different kinds of questions. So the important point here is really, in all these questions that I've listed here, is to ask what would happen if we change something in the world. So we are not merely asking whether two things are correlated anymore, right? And a Bayesian network can tell you that. Yeah, these questions are specifically asking whether an intentional change to one variable will produce a change to another variable. So that is the central, actually, in a nutshell, all of this, whatever I'm talking about in today's lecture, this is actually the central purpose of causal modeling. And this is why causal reasoning, the last two lectures in my PGM course is causation and then the decision making. Right? This is why causal reasoning is so closely connected to decision making. So a decision is, in essence, an intervention, isn't it? Did you see in the last lecture, normally I first teach causation, then I move to the structured decision problems. Right? This is lecture 9, but unfortunately, because the way things had to happen this 2 weeks, I had to put this one in the end, right? But it does make more sense to talk about causation before, because causal reasoning is something that you need to know or make sense of before you start talking about decision making. So in other words, the decision is in essence an intervention, if you think about it that way. Then we decide, so when we decide to prescribe a particular treatment or change a policy, introduce a fee increase at a university, or provide tutoring to students in computer science, we are actually asking what are the consequences of that decision. So in the decision scenarios of using influence diagrams, we looked at utility, right? Here we don't have the notion of utility. We simply are asking we're asking about the consequences of these actions. All right, this is very fascinating. If you can understand the difference between of this and the other lectures, then you will find it is a very useful tool in modeling and machine learning. Okay, let's look at counterfactual queries. So a second important type of causal query is the counterfactual query. So once you get this causal graphical models that we're talking about, you can get the intervention queries. You can also get the counterfactual query. So a counterfactual query asks about an alternate version of the world. So here we already know something about what actually happened, and we ask what would have happened if something had been different. For example, what would an accident still have occurred in the car, or if the car had been driven by a human instead of by a machine? Or if a car does not start but the lights work, would replacing the battery make the car start? Okay, these are examples in I've written them down here from the textbook. From the Collar textbook. So counterfactual reasoning is one of the most powerful parts of causality because it asks about specific cases, not necessarily about groups or populations. So, for example, in law, medicine, in ethics, we often we don't only ask whether the action usually causes harm. We ask whether the particular outcome would have happened if a different action was taken. You see, there's very different. It's a different kind of scenario. So counterfactuals are extremely important for responsible AI, right? This is what my lab is all about, for being able to produce explanations, even when you have a model which does very good with prediction, but it needs now to have responsibility. It needs to explain how did it make that particular how did it make that particular recommendation? So they need to allow us to ask, well, what this factor actually necessary? Was it actually necessary for the outcome in a particular case? Was this variable actually important? All right, okay, so this is a much stronger question than simply asking whether two variables are associated in the data set. I'm sure you noticed that already. All right, okay, so that's really nice. So now we're going to be talking about this in a bit more detail. So the philosophy of it, you understand it, I'm sure, and now you don't yet know how it looks in a model, but we'll get to that. So let's look at these toy examples first so that you really understand the intervention versus the probabilistic query, right? So, okay, So consider a very simple example involving students. Suppose we collect data on 100 students. We record how many hours each student studied. We record their test score and whether they received tutoring. So we have the variable x, which is the number of study hours, the variable y, which is the test score, the variable z, which is whether the student received tutoring. A probabilistic query might ask something like, what is the probability that a student who studied for 5 hours scored above 80%? An intervention query asks something different. It would ask, what is the causal effect of tutoring on test scores for students who studied 8 hours? It's a very different question. The first query is observational. The second query is causal. So in this example, it's useful because the variables look very simple, but the interpretation is not simple. Students who receive tutoring may differ from those who do not. They may be struggling more, they may be more motivated, or they may have better access to support. So the tutoring variable is not automatically causal just because it appears in the data set. All right. Yeah, okay, great. So now let's look at a probabilistic query. So for the probabilistic query, suppose 20 students studied for 5 hours, and 10 of them scored above 80%. Okay, then we end up with something like this. Okay, so this is the probability of y is greater than 80%. And x is equal to 5, right? So based on the observed data, a student who studied for 5 hours has a 50% chance of scoring above 80%. This is a standard conditional probability calculation. It does not tell us what would happen if we forced a student to study for 5 hours, okay? It only tells us what is true among students who were observed to have studied for 5 hours. So this is the key limitation of a purely observational query. It describes what we see in the data, but not necessarily what, it does not necessarily describe what would happen under controlled action. So very, very different. Okay, now let's look at the other side of the coin. Let's look at an intervention query. Suppose that 30 students studied for 8 hours without tutoring and had an average score of 70%. Suppose 15 students studied for 8 hours with tutoring and had an average score of 85%. If we assume that there are no confounding factors, and I'll explain what confounding factors are later on and more technically, but for now just think of them as other variables inside that we do not directly observe, then the causal effect for tutoring is the 85% minus the 70%, which is 15%. So under the simplified assumption, tutoring actually increases the average test score by 15 points. All right, so that's an interesting kind of a way of thinking about it here. There's different scenarios. Okay, the assumption is important. If students who receive tutorings, the assumption that we said about the confounding, right? It's important because students who received tutoring already might have been more motivated or had better prior knowledge, then the difference may not be caused entirely by tutoring, right? So understanding what variables are around the context of the scenarios is extremely important, right? So these are the confoundings. So I'm gonna now talk a bit more about that, right? So before I do, let's talk about real studies, right? So in real studies, the phrase assume there are no confounding factors is actually doing a lot of work. It is often the strongest and most controversial part of a causal claim, and this happens often in machine learning, where they say, let's assume that those other variables are not really present. They're not affecting the particular outcome. So the numbers may be easy to compute, but whether they actually have a causal interpretation, this really determines the structure of the problem. So let's talk about these confounding factors. And well, we first got to start with some basic correlations. Okay, so when two variables are correlated, there are multiple possible explanations, right? So you could have this scenario. It may be that x causes y. It may be the second scenario that y causes x. It may be this third scenario, or this way we have a new variable z, which causes both x and y. And that's, yes, you can make x and y correlated, as you know from the first lecture on Bayesian networks. So the third variable here, the z, this is our confounder. Can you see it's a variable that's there, where we might necessarily observe, we might not necessarily observe, but it influences X and Y to the extent that they become correlated. So this is called a confounder. So a confounder can create a correlation between two variables, even when there is no direct causal relationship between them. This is why correlation alone is not enough for causal reasoning. A useful phrase here is a confounder is a common cause. Right? This is what people say. It's a common cause that creates a misleading story. We'll look at examples of how that is actually the case later on in the next few slides, actual real life scenarios, and there's very famous ones too. So the dangerous thing about confounding is that the story often sounds very plausible. For example, if people who take Gaviscon, I think I have a nice example there. Yeah, it is. Okay. So people who take Gaviscon, and Gaviscon is it's an antacid, right, are more likely to have stomach ulcers. It is tempting to say that Gaviscon causes ulcers, right? You see the Gaviscon here causing the stomach ulcer. It's very tempting to do that because these two things are correlated. People who have stomach ulcers often take Gaviscon. Or yeah, all right. There's a correlation there. But the most sensible explanation is that the stomach acid causes both the ulcer symptoms, right, which is here, the stomach acid, as well as the decision to take Gaviscon. So causal modeling often protects us from telling the wrong story about the data. And we'll look at that again when we talk about Sampson's paradox. So the whole story behind this confounders, and before I talk about selection bias, right, is that latent variables make the problem harder. That's really what this was. This was a variable that we didn't really observe, but it actually made some of the variables inside of my study correlated. So that makes it very difficult because now how do I know that I'm deducing any kind of causal explanation? This is one of the reasons this is a very difficult problem. And so latent variables make the problem very hard. A latent variable is a variable that affects the system but is not directly observed, right? So that's really the definition of it. And for probabilistic queries, we may still be able to answer questions if the marginal distribution is correct. But for causal queries, hidden confounders are dangerous because they can make us misinterpret a correlation as a causal relationship. So the Gaviscon stomach ulcer example really illustrates this. And the difficulty happens in the complex real-world systems. We really know every relevant latent variable. And this means causal reasoning is never just a mechanical statistical procedure. It requires domain knowledge, assumptions, careful modeling of the problem with all possible confounders, or the important ones that can sometimes deceive us. Okay, so that brings us to selection bias. So in selection bias, this occurs when the data we observe does not represent the true population. So let's look at an example. Suppose WIT sends a survey to alumni about academic and sporting activity. The results show a negative correlation between sports and high marks. All right. So one interpretation of that might be that sports reduces academic performance. Okay, another interpretation might be that students with high marks tend not to participate in sports. But there is another possibility. Perhaps the people who responded to the survey are not representative of all the students. And so the observed relationship may be caused by the sampling process rather than the real causal effect. And this is interesting, right? I mean, look at that. We're just collecting samples sometimes causes the bias to occur. And so selection bias here is especially important when we speak about causation because so much modern data is passively collected, right? You'll find this, like for example, the Ray-Ban glasses, right? Who buys the Ray-Ban glasses, right? To collect data on that. What population group does that? And so who has responded to the WIT survey, right? The ones who check their emails maybe, right? Should that be something that we include in the causal model? So things like online reviews, social media posts, survey responses, app data even on your phone, and even university feedback forms are really generated by a perfectly representative population. And that causes the selection bias. So people who respond are often those with very strong opinions, unusually positive experiences, or unusually negative experiences. So when we build models from such data, the model may learn the behavior of the observed sample rather than the behavior of the true population. This is one reason why big data does not automatically mean good data, right? Some people, they get very impressed by having billions of samples, okay? That doesn't necessarily say much about the quality of the data, given that selection bias is a big thing. All right, so the point on this slide about selection bias is that the respondents may be an unusual segment of the population. So perhaps only students who are very successful academically or very successful in sport chose to respond to that survey. Students with average experiences may have ignored the survey. If we do not account for the selection process, we may falsely explain the observed correlation using the causal story. This is why we must be careful when using observational data for causal claims. And that's what makes this a very difficult problem, the fact that we're using observational data to tell a causal story. So a useful way of thinking about selection bias is that the data collection process itself becomes part of the causal system. Although we don't note it in any way, but it is indeed part of the causal system. We are not only modeling the variables we care about, we also need to ask why some observations appear in the data set and not and other variables do not appear in the data set. All right, okay, so let's look at other factors. And these are all other things that, these are other reasons why non-causal correlations can appear. So a common cause may influence two variables. We spoke about that. Noisy data may produce patterns by chance. That's interesting. Data mining can produce spurious associations because many relationships are tested. Measurement errors can introduce false patterns. Time-related trends can also make two variables move together without one causing the other. The general lesson here is observed associations is only a starting point, and it is not enough to establish causation. So this is because, especially important in machine learning, because a predictive model can exploit any statistical pattern that improves accuracy. Right? This is true for neural networks specifically. So even if the pattern is not a causal pattern, it'll still exploit those so that it gets a high accuracy. And this is why a model may perform well in one environment but fail when deployed in a new environment where those non-causal correlations no longer hold. So this is like taking what you know about training, the kind of learning aspects of the machine learning stuff you learn, even in your other courses other than PGMs. I know we had a whole lot of lectures on learning, but in your other lectures, when you're talking about optimization in a particular machine learning paradigm, bear in mind that while the model that you train performs really well and it fails in a new environment, sometimes it's because it's making assumptions about variables, right? And that are not true. It's making assumptions about causation between variables that is not true. And since those causal relationships don't hold, the model performance suffers. Okay, so now we get to Bayesian world again. So we're going now back to causal models. So we're getting back to the graphical models kinds of things. So we had to do all of that preparation first because we have to debunk all of these issues we have about training data, about confounding factors and so on. So we had to do all of that. Now we've got ready, we can now start with graphical models again. All right, so let's now introduce the idea of a causal model. So what is a causal model? It can be viewed as a Bayesian network with causal semantics. So each variable is governed by a causal mechanism. This mechanism determines the value of the variable based on the value of the parents, just like we did before. The edges represent direct causal relationships, so this was not as before. Before it was just correlations. Now they are directed causal relationships. And causality flows in the direction of the edges. So there's a literal flow of causation in these arrows now. So for example, age may influence experience, education may influence income, The experience may also influence income. Education influences income, age experience, I think I said all of them. Experience also might influence education. Right, so these are all the causal semantics of this model. All right, so the only addition here is the interpretation, right? So in ordinary Bayesian networks, an edge represents the dependencies, the conditional independencies, and you can write them out as independence assumptions. Even without the graph, you can write down the independence associations. But in a causal model, an edge represents a direct causal mechanism. So this is a much stronger claim, as you might have realized. It's a much stronger claim to have. All right, so let's talk a bit about intervention queries versus probabilistic queries. We're going back now to what we spoke about before, but now we're going to be more technical in the view of this graphical model. All right, so okay, so this example uses the student model that we saw in previous lectures, and obviously there we had the variable for difficulty, intelligence grade, the APS score, and the job outcome. So let's suppose that SIPO gets an A. If we observe that SIPO got an A, then our belief that SIPO is intelligent increases. Our belief that SIPO had a high APS may also increase. Our belief that SIPO might get a good job may also increase. Right? Okay, so that's really nice. But now suppose a different scenario, that SIPO bribed the professor, okay, to get an A. I don't know what he did, right? He bribed the professor fell for it and gave SIPO an A. Maybe it was a bribe, I don't know, could have been blackmail, right? I don't know. Okay, in that case, the grade has been manipulated, which means that grade no longer gives us evidence that SIPO is intelligent or that he had a high APS. Okay, so somehow the parents of grade are now no longer influenced by the grade going up, because it shouldn't, right? I mean, in a causal interpretation, if the grade goes up, then we're forcing, remember we use the word force, we force the grade to go up. But if we force something, or if we bribe the professor and you write down the grade that's not true, then it shouldn't change the parents, because the fact that the course was difficult doesn't change just because SIPO bribed the professor to get a grade. The fact that the intelligence of SIPO can't change because he bribed the professor to get a good grade. So the parents now are no longer of grade, should no longer be swayed by the grade changing. All right. So however, the manipulated grade may still affect the job outcome, because obviously now it's going to be written in his transcript that he did well for the PGM course. It's going to be written that the job person will see that good mark and might just take it to be true, because WITS is a reputable university and it says, oh, SIPO got an A, that's great. Well, let's hire him. He must be very smart. So the intervention affects descendants of the intervened variable, but does not flow backwards to the causes. So that's the big claim. So this example shows why the causal direction matters in the previous slide where we had those arrows. So if we observe that SIPO has an A, we may infer that he is intelligent. The grade gives us evidence about his intelligence. But if we force the grade to be an A, then that evidence disappears. The manipulated grade no longer tells us that SIPO is intelligent or that the course is difficult. So this is really the basis of the distinction in explainable AI, in causal modeling. A model may discover that a variable is predictive, but it does not mean that the variable is causally meaningful. So good explanation should therefore distinguish between does help the model predict the outcome and does actually cause the outcome. All right, so this is a very important distinction. All right. Okay, so to answer an intervention query, we modify the original causal network. So we call this the mutilated network. So remember I told you that the parents of grade now are not influenced. So we take that quite literally. And so we sever the connections. So we mutilate the network so that we can sever the connections between grade and the parent, so that the influence can no longer flow upwards. So to get the causal explanation, we sever those connections, like as I said, by mutilating the network. All right, so the modified graph is called the mutilated network. shown on the screen. So when we intervene on CPO's grade and force it to be an A, we remove the normal causal mechanism that determines grade. We replace it by an external intervention that sets the grade directly. So this is why incoming edges into the intervened variable are removed. The intervention breaks the normal causes of the variable, but the variable can still influence its descendants, right? So boss will still get, or the job interview guy will still get that grade. So this is the graphical meaning or the structural meaning of the do operator. So this is what really makes this different. This do that we saw before. All right. What else can I say about this? Okay. All right, so let's just say that in this example, grade no longer depends on difficulty and intelligence, but grade may still affect the job outcome. The intervention changes only the mechanism that produces the grade and doesn't erase the consequences of the grade. So that really is the message here. Okay, so now let's look at this, a really cool example in probabilistic modeling. And it really shows us how aggregated statistics can be misleading. And we'll use this example later on when we talk about specific rules in causal reasoning and applying those rules. So we can use this one as a running example. So suppose that 60% of patients who took a drug was cured. Okay, so that's written down there. Only 40% of the patients who did not take the drug were cured. At a first glance, this statistic kind of infers that the drug is beneficial. But then what happens when we look at it by gender? So we'll see I've separated it by male and female. So among female patients, 75% who took the drug were cured, but 100% who did not take the drug were cured. Among male patients, nobody who took the drug was cured, but 25% who did not take the drug was cured. So now the drug looks beneficial overall, but harmful within each subgroup, right? Because the first, in 1 and 2, it was beneficial, but in 3, 4, 5, and 6, it was harmful in the subgroup. It looked like it was doing worse. So this scenario, and obviously you can explain this in many different ways, not only in a medical example, but this scenario is called Simpson's paradox. And it's interesting because it shows that more data can sometimes make us more wrong. So when we combine all the data, the drug appears beneficial in 1 and 2, but when we look within the relevant subgroups, the conclusion reverses. So the problem is not that the percentages were calculated incorrectly. The arithmetic is correct. The mistake is really the causal interpretation. This is why the structure of the model is very important, and I'll show you an example of the structure on the next slide. So, yeah, all right, great. So let's look at this a bit closer. So this is just explaining the same thing again, but using actual numbers to show you that the math is all correct, because I said that on the previous slide. All right, so then this shows the actual count. So overall, 3 out of 5 patients took the drug and were cured. Oh, sorry. 2 out of 5 patients who did not take the drug were cured. So overall, the treatment works, okay? But when we split it by gender, as you can see in the different picture at the bottom, for females, the cure rate is higher without the drug. For males, the cure rate is higher without the drug. Right? So the paradox arises because the treatment groups are not balanced across gender. There's an important lesson here, and it's the aggregation can hide the aggregation here. When you join the statistics and ignore the gender, it can hide the structure of the data. So once you condition on the relevant variable, then the causal story completely changes. So when we condition on the gender variable in this case. Okay, great. So then let's talk a bit about Simpson's paradox a bit more. So the problem really is, in essence, right, what Simpson's paradox actually does, it tells us that taking the drug is correlated with gender. Right? So these two variables are correlated. And so women are more likely to take the drug than men in this example. So the overall treatment statistic mixes together these two things, the effect of the drug and the gender distribution of the patients. And the question is therefore not whether the probability of being cured given the drug is greater than the probability being cured not given the drug. The causal question is whether the probability of the drug, the probability of being cured, if we force the drug, that's the question. So here it is: the probability of being cured if we force a person to take the drug. If we force a patient to take the drug. And to answer that, we need to be able to derive the mutilated network from this. So this is our structure. We then have to derive the mutilated network to get this one. And then from here, we can be able to calculate that. So what is this asking? It's asking what would happen if we intervened and prescribed the drug and it was taken. So this is a very different kind of shift. It's a conceptual shift. We're not asking anymore, among the people who have happened to take the drug, how many were cured, right? That's what we would be asking in a Bayesian network. We are actually asking here, if we assign the drug, what would the cure probability be? That's really what we're asking here. It's a very different kind of question. All right, so let's talk about this a bit more. So now we've mutilated the network, we've removed the association from gender to drug, and we intervened on the drug variable. So that little double line around the drug variable means that we are doing an intervention. And so the intervention now is, there's this double line here. That means that we've got to sever all of the parent connections. I'm sorry, let me just cough. Perfect. All right, so gender can still affect the cure. The drug can still affect the cure, but gender no longer determines who receives the drug. Right, that's actually what happened here. So this is, if you know anything about sociology, this is basically what a randomized controlled trial does. It tries to break the link between different variables. And by breaking this link between gender and the drug, in this particular case, we can isolate the causal effect of the drug. So the mutilated graph is not only a mathematical trick, it captures the logical intervention, right? The causal logic. There's an honors student of mine who's doing causation, and he's very fascinated about the way these causal mechanisms work, and he's learning about it for the first time. And every time he comes back with new ideas, it's just because all of this is so hard to grasp when you see it for the first time. But once you get it, right? So you just have to keep at it and just keep looking at this and trying to convince yourself, obviously with evidence, that this mutilated graph actually does capture the logical intervention. And that it isolates the causal effect correctly. That if you can do that, then I don't think you'll have much problem with causation, because that's really what you'll see. The rules that come out of this is all centered around this exact idea. So it tells us which causal mechanism can be replaced and which mechanisms remain active. In essence, it's a very important way of. So in graphical modeling, what makes it explainable is this. Well, the graph structure helps, right? But having an explicit way of representing variables and the way they're related, right? For example, if anyone's here used principal component analysis, you'll realize that those vectors are an amalgamation of lots of variables. And to be able to tell what's going on there, it's extremely difficult. But here in graphical models, and you can have a PCA kind of a model that represents that as well. But here we have a very explicit way of identifying relationships. And so what makes graphical models powerful is being able to interpret the model in an unambiguous way. And that's exactly what causal graphical models help us do. It helps us represent very complicated things. For example, in this case, breaking the link between gender and the drug, isolating the causal effect in this way, it allows us to do this in a very visual way. So we can actually show it to someone and say, hey, look, this thing makes sense. And you can use it for your problem. And you won't get any weird results because it makes sense. So yeah, so that just I just had to put a bit of 2 cents in there because it's important that everybody gets that, at least understands the power of this framework that I'm teaching you. It's extremely powerful, and it's something you must know. Very few people know about graphical models, and it's such a shame. And I know it's difficult, but it's a very powerful technique. All right, great. So let's talk a bit about the structural causal identifiability. So now this is now the sad story. Okay, so far we assumed that we always had a fully specified causal model, but obviously in reality, fully specifying a causal model is often impossible, right? Finding all of those confounding variables. There may be latent variables, unobserved mechanisms, missing causal relationships. You could have the selection bias on one side. So there's a lot of major questions. So one of them is, can we still answer causal queries using only observational data? All right, because with interventional data, the problem is solved. Causation is no longer difficult. But with observational data, the question is, can we answer causal queries using only observational data? So the answer is not no, surprisingly. It's sometimes. Yes, you can. You can. Sometimes you really can. Identifiability asks whether a causal query can be expressed entirely in terms of observable probabilities. And if it can, then we can estimate the causal effect from the data. If not, then the causal effect is not identifiable and without additional assumptions. Looking at the previous scenario here, we have this particular causal query. So the question is, can we calculate this? We've got everything we need right here. We've got this variable gender, we've got this drug, we've got this this factor which has to do with all three variables. And then the question really becomes, can we answer this? And how do we represent this? Right? So yeah, so sometimes we can, right? And we know where we can and we know where we can't. And there's still some gray areas, but yeah, if we can, then we can estimate the causal effect from the data. If not, then the causal effect is not identifiable, right? Without additional assumptions, which is what you could you could assume. Other things like this association is not possible, or that these values are not always present, or they are no longer any confounding factors, and you know that for a fact. All right, so these are horrible assumptions to make. But identifiability is really one of the most important ideas in causal inference. So it tells us whether the answer to the causal question is even available from the data that we have, all right? And obviously this is important because not every causal question can be solved by collecting more observational data. So no matter how much data you have, you might never be able to answer some causal queries. Sometimes the problem is not even the sample size, sometimes it's structural. So even with infinite data, the causal effect may remain unambiguous unless we run an experiment with interventional data and measure additional evidence or variables to make, or even make stronger assumptions. Right? So this is quite interesting. Okay, so identifiability is like a warning system, right? It tells us when data is not enough, when having more data might not help us, and things like that. It also has to do with whether we can actually deduce the causal kind of the structure of the causal the structure of the causal effect. If you can even do that, because in a Bayesian network, I'm sure you noticed, you can represent the same kind of independence assumptions with completely different structures. And those identifiability then becomes problematic, because then there might not be anything that you can know that will help you choose one structure over the other. Remember when we did structure learning, what we ended up with was a I-equivalent class of structures. And there we just pick one and use that structure, whereas all of them gave you the same BIC score or the same likelihood score. There was no way of choosing the correct one. All right, so it's quite problematic. All right, so this is where the query simplification rules comes from. So the causal graph gives us the rules for simplifying intervention queries. You can think of it that way. So these rules can sometimes transform a causal query into an ordinary probabilistic query. And how do we solve an ordinary probabilistic query? We use variable elimination. We use approximate inference. We use particle-based inference, right? All of the things we know about, because we know all of that stuff that can help us with probabilistic queries. All right, so and as we know, ordinary probabilistic queries can be answered with ordinary observational data. Right? So that's super easy. You just learn the parameters from the observational data, or whatever form it takes, and then use those in variable elimination. So the rules that I'm going to show you are based on an augmented causal model where interventions are represented explicitly in the graph. And I'll show you the notation for that. So we introduce a decision variable, right, written as Z with a little hat on top of it, like that one, which controls whether Z behaves normally or is forcibly set to a value. So we do this because it allows us to use deseparation to reason about interventions. Deseparation, remember, in that lecture on Bayesian networks, it tells us what is directly separated. Remember, then we had these colliders and these V structures, where correlations worked in a specific way with the variable Z. All right, so anyways, we're going to remember those rules, and we are going to try to make sense of some examples. Okay, so the broad idea here is that graphical structure gives us now an algebraic power, because with these augmented causal models, with the Z hat, we now can use a very structured language to isolate particular scenarios, and with those apply these rules, which I'm going to show you now. And and then you can simplify very complex causal queries into perhaps observational queries, probabilistic queries, and then answer them as we know how to answer them. Okay, great. So that's the big idea. Let's do it. Let's start with the first rule. Okay, I've made up these names. Okay, and obviously, depending on which book you read, you'll find different names. I just made up these. They made sense to me when I wrote them. Otherwise, I don't want to just call them Rule 1, Rule 2, and Rule 3. So let's call Rule 1 a graph-dependent intervention rule. So all this one says that under certain deseparation conditions, we can remove the observed variable W from the query, and we get this. So we end up with the probability of Y given, if you have these as the intervention variables, some evidence and another set of evidence, then you can get this, right? You can completely remove W. And this is only if Y is deseparated from W, but these ones are deseparated from W, given this evidence, Z and X. So this is just normal stuff, deseparation, where you have, this is the observed class, it's just X and Z, and you want to see if this set Y is deseparated from this set W. And so you trace it in the graph, and I've color-coded it to help you. And if you can do this, if you meet this definition, then you can take out W completely. All right, the intuition here is very easy. It says that if W provides no additional information about Y, once we already know the intervention, then the other evidence, then W can be removed, right? So it doesn't give us any value, in other words. So it tells us that some pieces of evidence are irrelevant in a causal query, and we can just throw them away. All right, so let's look at another one. So this rule, we'll call it the information conservation rule, right? And here it tells us when an intervention can be replaced by an observation, which is pretty cool. In other words, under certain graphical conditions, right? So the do here of X can become a normal observation. Isn't that cool? This can be simplified, and we'll use this rule later on Simpson's paradox later on, right? So, but look at this. You have one with the do, and then you have one without the do. And the intuition here is that the intervention at x provides no additional information about y beyond the value of x itself. So before, in the first rule, we just got rid of it. But in this rule here, there's no additional information other than just the value of observing it. That is x. So this rule is extremely important and very useful, as it helps us to convert a causal explanation into observational ones, right? And this is where identifiability starts to become practical. So the stuff I said about identifiability. If we can replace the interventions or observations under the correct graphical conditions, then we can estimate causal effects using ordinary data. Right? There's really no reason to get fancy. If we can do this a lot, then we'll always just need ordinary data, but for X, and not any crazy stuff with interventions. Okay, great. So that's rule number 2. So let's look at rule number 3. So rule number 3, let's call it the irrelevant intervention rule. And this one tells us when an intervention can be removed completely. So that's pretty cool, right? So we see here your intervention didn't just become an ordinary observation, but instead it was deleted. Okay. Okay, great. So what did I want to tell you about this one? Okay. So if y, and you can do this if y is deseparated from x hat. Okay, where's x hat? Here it is. These red ones. Given z, which is the blue nodes, w, which is the green nodes. Okay, so that's when you can use this one, and so you can remove both the intervention and the value of x from the query. So the intuition here is that changing x does not affect the outcome we care about, which is the specific causal query. So given the structure of the graph and the information we already know, it doesn't really change anything. This is another example of why causal graphs are valuable, right? They show relationships, sure, but they also tell us when some relationships are irrelevant for a particular causal query. All right, so then that's really the 3 rules, right? And so now we're going to use these rules. We're going to apply them to Simpson's paradox. So the causal query from before was the probability of to cure given that you take the drug. And you can write this out using by conditioning on gender, okay, and we end up with this. Then you can use the second rule, which is the information conservation rule, which says that you can convert this do into an ordinary evidence that we can learn with ordinary data. Okay, and then so using rule 2, we replace the intervention with observation inside each gender group because the condition is met. And this changes the formula to this. The do no longer is here. Okay, so that's pretty cool. And so now that we have, now that we are here, we have set now just an ordinary evidence. Excuse me. We then can simply do the calculation. Now we can just simply calculate the causal effect. So for the drug condition being cured, whether you take the drug or not take the drug, if you take the drug, you have a 0.375% chance. Sorry, that's not a percentage. It's a probability. And if you don't take the drug, you have a 0.6. So what does that mean? Is the drug beneficial or not? Okay, so you can be cured if you don't take the drug with a 0.6 probability, which is pretty good. So the probability of cure is higher when we don't prescribe the drug. Therefore, the causal conclusion is that we should not prescribe the drug, okay, according to our causal equations. All right, this is really the opposite of what the aggregated data suggested. So you see, this is gave us valuable information. And from my lecture on decision networks, influence diagrams, remember, information is valuable when it changes your decision. So does this change your decision? Yes, it does. Before, we didn't know what to do. The data was saying take the drug. the model was saying take the drug. When we ran the causal query, it says don't take the drug. So indeed, whether to take the drug or not was our decision. Then this kind of evidence does change the decision. And so there's a key lesson here from this calculation, right? It's that the correct causal estimate is not necessarily the overall average. So instead, we adjust the variable that affects both the treatment and the outcome, which in this example was the gender. We isolate the causal connection, and then we compute it using causal inference. All right, so here we're not really controlling variables blindly as we did before. We are really controlling the variables in a structured way using a causal mechanism, isolating the network, mutilating the network, and then answering the query. The isolating part comes from the rules that we establish. All right, very interesting, and I hope you find this valuable. Okay, so now let's talk about now where we can and where we can't be able to identify a particular causal estimate. All right, so on this slide, we show examples where the causal effect of X on Y is identifiable, right? See at the top. And on the next slide, we'll show where it's not identifiable. So look, I mean, you don't have to memorize this graph. It's very difficult. And plus, I put it on the formula sheet anyways, right? You just have to understand the principle. In some graph structures, even with additional variables, the causal effect can still be expressed using observed probabilities. So this is those examples. This usually depends on whether we can block backdoor parts or adjust the appropriate variables or simplify the intervention query. And so again, identifiability is a structural property of the graph if we can do this. So before you ask whether you have enough data, you should first ask whether the graph allows a causal effect to be identified at all. And if it matches any of these, then it does. On the other hand, in these cases, the graph contains structures that prevent us from uncovering the causal effects using observational data alone, right? So here, the dotted lines indicate a common effect. So for example, from X and Y, in the first one, there is some latent variable which is affecting both Y and X, like a Z. There you can't determine the causal pathway. All right, so this means that two different causal models could produce the same observed distribution but imply completely different causal effects. So the data alone is not enough, and you need stronger assumptions or more variables or more, actually just intervention data in these cases. So this is an important limitation, right? And it's good to know when you have a lost cause on your hands. So it means that causal inference is not, it is difficult, but it's not impossible. It's not magic, right? There is a very structured way of answering causal queries, and they can be done in cases where you have observational data. And sometimes we know when we can't. Okay, great. So that's normally when I would tell you to take a break. So if you want to pause the video and take a break, do so. Yeah, and then we can move on to the mechanism and response variables, which is now in a different way, a different kind of causal model called a functional causal model. And yeah, all right. So you can pause it for a few minutes and then you can come back again. Okay, so I had to take a break too, so I just got back. All right. Now we move to this idea of functional causal models. So this is really, if you meet the big causation researchers, one of my students is studying in Barcelona now. There's a lab there, and he's being supervised by this causal guy. And he is publishing in the big venues about causation, and it has to do with a functional causal model. So at least that's what his PhD is about. I haven't spoken to him about a few weeks ago. And he is looking at, for example, using functional causal models. He's something about using it in the context of robotics. Also constructing causal graphs from observational data and stuff like that. Okay, so it's a very powerful framework, right? So I'll explain what it is, and then yeah, if you want to do advanced work in this area, Yeah, you can. So a functional causal model it's more detailed than the standard causal graphical models we were looking at now, right? So a functional causal model, so instead of saying that a variable depends probabilistically on its parents, what we do here is we explicitly model the mechanism that determines the variable. And this is important in something called counterfactual reasoning. Remember, we said there's two queries that a causal model can answer. The one is the interventions, the other is the counterfactuals. Well, this is where the counterfactuals come in. And we'll see examples of that later on. So to answer counterfactual queries, we need to distinguish between endogenous and exogenous variables. Endogenous variables are inside the causal model, right? And the exogenous variables represent background factors and stochasticity from outside the model, okay? And so the idea here is really that the functional model allows us to preserve these background factors, right, which is the exogenous ones, when we move to the real world, to the counterfactual world. So that's really what we're trying to do in a functional causal model. So functional causal models are interesting because they move us from population level causality to individual level mechanisms. And remember, we said that's a big advantage of using a graphical model in the first place. And the standard causal models might tell us that treatment increases the probability of recovery, but a functional model can tell us, it'll allow us to represent different kinds of individuals. Some people would recover regardless of the treatment. Some recover only if treated. Some may be harmed by the treatment. Some may not recover at all. Either way, right? No matter what happens. So it kind of looks much more closer in how real systems behave. So in medicine, in education, sociology, economics, in the social systems in particular, people do not all respond in the same way to the same intervention. A lot of people respond differently. And so we need to capture that. And the functional causal model allows us to do that. Okay, great. So a very important part of the design of a functional causal model is a response variable. So let's look at SIPO again. And suppose G is the grade and J is the job outcome. So look, it's just two variables. So the job outcome is a function of the grade and some exogenous variable U. Right, so we got it written down there. So it's explicitly modeling this exogenous variable, which is the background. So the response variable, so we're talking about this one here, okay? The response variable encodes how the individual would respond under different values of G. Right? So in the back of your mind, you're like, oh, I've seen this before. It's a factor, but it's a very specific kind of thing. So for example, some individuals would get the job regardless of the grade. Right? Some people would get the job only if the grade is high. Some people may not get the job regardless of the grade. So this is the reality, right? This gives us a more detailed representation of the world. It gives us a more fine-grained one. It's an individual level causal behavior, if you think of it that way. So the response variable is therefore a compact way of representing all the possible ways an individual could respond to an intervention. So that's what you see on the screen. And this is why functional causal models are especially useful for counterfactuals, because they don't say what just happens, but they ask what would happen if, for this specific individual, if this particular variable changes. So that's pretty cool. So these are all of the different cases, that the different worlds where the student with different grades either gets the job or doesn't get the job. It looks a lot like the factor. All right, so let's look at an example of this in a clinical trial. So on this slide, we apply a functional causal model to a clinical trial. So there is an assessment variable, an assignment variable. You know, there's so many different names for things in causal modeling, I get confused sometimes. So this is a clinical trial. So there must be an assignment of a drug. There must be a treatment. There must be an outcome, right? So that's what a clinical trial specifically encodes. And an assignment variable indicates whether the patient is assigned the medication or the placebo. You know, in a random control trial, they sometimes just give the person a white tablet, and it could be either a sugar tablet or it could be the actual medication. And then they try to observe the effect after that. So everyone gets a tablet, but whether it's the medication or the placebo, there's an assignment variable that tells us. So that variable, the assignment variable, indicates whether the patient is getting the actual medication or the placebo. But assignment does not always determine the treatment. Some patients comply, some always take the treatment, some never take the treatment, some do the opposite of what they are assigned because they're troublemakers, right? But what's nice about graphical models is that we can capture that. But this is captured by the treatment compliance model, and that is what you see in front of you. So there's a compliance model there. The outcome response model then describes how the patient type responds to the treatment. And so you can see that this is a much richer than a simple model that only asks whether the treatment and the outcome are correlated. Right? It's much more complicated. So, for example, a complier follows the assigned treatment and always takes the treatment regardless of the assignment. A never taker refuses the treatment regardless of the assignment. A defier does the opposite of what they are assigned to do, a defier. So these categories tell us they are separate assignments from actual treatment behavior. And in real clinical settings, what patients are assigned and what the patient actually do are not always the same thing. All right, and this model actually captures it in a very nice way. All right, so then let's look at what the counterfactual query actually is. So we're going to turn our attention to the counterfactual kind of reasoning. And a counterfactual query asks us to reason about two worlds at the same time. So first, the real world, where we observe what actually happened. And second, the counterfactual world, where we intervene and change something. The key assumption here is that the same response variable are preserved across both worlds. Whether that is a reasonable assumption, I don't know. But that's generally what is assumed. So if we know something about the patient's type in the real world, that information carries over into the counterfactual world. So the query on this slide, at the bottom here, right, it asks whether a patient would have been healthier if they complied with the treatment, given that in reality they did not comply and did not get well. Okay, so you see, this is now reasoning about two worlds at the same time. At the same time, because they are on the same query, those variables are all exists on the same query. So that's what at the same time means. But two worlds, because we have different kinds of variables, and some of those variables are from the one world, and some of those variables are from another world, which has a complete setting. I'll show you what the causal model looks like on the next slide. And this is extremely different from asking whether treatment helps people in general, which is what the standard causal model could only do. All right, okay. So here we're asking, would it have helped this specific patient who would have been healthy? Would have is counterfactual. Would have been healthier if they complied with the treatment. But in reality, they did not comply with the treatment and they did not get well. All right, so then that brings us to the twin counterfactual model, which is what this thing looks like. So this is the twin counterfactual model, and it represents the real world and the counterfactual world side by side. So you'll find the probabilistic query at the top actually contains variables from both sides of the different worlds. And the real world contains the actual assignment, the treatment, and the outcome. The counterfactual world contains the modified version, where we intervene and we set the treatment to T1. All right, so there you see the blue at the bottom there is setting the treatment. And see where we set the treatment, we do an intervention, and that severs the parent to treatment. I think my notation wasn't very good here because they all look like interventions with dotted lines. But yeah, it's just the treatment that should be dotted, not dotted, a double line. Okay, great. So that's really nice. So what is the point of all of this? It's that the two worlds share the same exogenous variables, which are those U's. Okay. And that is why the model can reason about the same patient under two scenarios. So that's actually what helps us with this whole idea. So that's what makes counterfactual reasoning different from simply asking about another randomly selected patient. The twin counterfactual model is quite elegant, right? Look, it models everything in a graphical model. We have both of the different worlds. We have ways of doing interventions in this counterfactual scenario. And we have notation for everything. It's a very elegant design. This is the power of graphical models. So it says that when we ask a counterfactual question, we do not just imagine a completely different person in a different world. We should imagine the exact same person in the alternate version of the world. And this is why the exogenous, I said this already, exogenous variables are the same, and they shared, the same exogenous variables are shared between the two scenarios, right, the two different worlds. So that means that the patient's underlying type, background, the response pattern remain exactly the same. Only the intervention is what changes. So this makes counterfactual reasoning powerful in graphical models. All right, that's really great. So now the question is, how do we compute it? So this slide just shows the actual counterfactual inference from, and we can then reduce it into the smaller table and then answer probabilistic queries, and it's all fairly simple, exactly how we did it before in the other lecture on probabilistic inference. Right, so actual counterfactual inference is easy. From the real world evidence, we narrow down the possible reasoning types. If we know the patient was assigned the treatment, which is did not take it, or it did not get well, the patient did not get well, and we just restrict the possible values of the treatment response and the outcome response variable. Then in the counterfactual world, we set the treatment to T1 and ask whether the outcome would be positive. And so then the final answer would be 0.77. All right, that's fairly simple. It's all just probabilistic inference. I hope you can do something like this in the exam. Just practice it. So given the model and the evidence, there is a 77% probability that the treatment would have helped, which is helpful. I mean, and it also shows us whether we should have assigned the treatment or not. The should have, could have. I hope no one says it's not too late to do it, because there's always something we can learn about having regret. So the important thing here is that we get a numeric answer, and also that there is a very explicit reasoning process that we followed, and it's a principled process that we can actually trace. And we use evidence from the real world to infer something about the patient's hidden response type. Then we carry that hidden type to the counterfactual world and apply the intervention, and then you get an answer. All right, so this is basically the process of counterfactual reasoning in graphical models, which is the cutting edge framework for this kind of practice. This is what people do. Anyone who's doing causation research does it most probably with graphical models, and they model it in this particular way using these twin counterfactual models. All right, this is the state of the art. 2026. Okay. You don't see a lot of this kind of research happening. I mean, I just told you one of my students is doing this, but you know, this is difficult kind of research. This is not the easy apply a neural network to a problem and then see what happens, right? This is functional causal models is so fine-grained that it gives a robot a way of having regret and making better decisions. All right, great. So let's talk about learning causal models. We never spoke about this. So now let's discuss, how do we learn a causal model from data? So look, I mean, there are several learning problems. You may want to learn parameters. You may want to learn response variables for a functional causal model. You may want to learn the actual causal graph structure. You may have what is observational data or intervention data or mixture of both, and you want to learn parameters with that. So the problem is difficult because a confounding variable, a latent variable, and uncertainty about the edge direction and what priors do we incorporate, these are all things that make the problem difficult. And so there are two important assumptions when learning causal models. There's the causal Markov assumption, and then there's the faithfulness assumption. And these, so the first one, the causal Markov assumption, that means in the true distribution, each variable is conditionally independent of its non-effects given its direct causes. This one makes sense. It's like basically the chain rule for Bayesian networks. It says that every variable is independent of its non-descendants given its parents. Okay, and then the faithfulness assumption is only conditional assumption independencies in the true distribution are those that arise from deseparation in the corresponding causal graph G star. So this really means that the structural assumptions made in G star are faithful to what's actually going on in the true distribution P star. Right, so in other words, G star is a perfect map for P star. If you forgot what that means, you can go back to the lecture on Bayesian networks. Right, it fully captures all of the independencies in the underlying distribution P star. All right, so together these assumptions allow us to connect. Oh, sorry, there was a yawn. So together these assumptions allow us to connect conditional independencies in the data to deseparation in the graph. Okay, so this is important, you know, I'm sure I don't have to tell you that already structural learning was difficult, right? There were so many different ways of finding a structure using score-based structural learning and constraint-based approaches. Well, learning causal models is a lot harder than learning just predictive models. Right? In predictive models, we are asking, does this model produce accurate outputs, you know, in terms of accuracy, in terms of F1 scores? Huh? In causality, we're asking, does this model represent the correct data generating process? That's a different question entirely, right? The correct data generating process. So these are not the same thing. A model can be highly predictive while still being causally wrong. For example, it may rely on shortcuts, proxies, confounded relationships. Remember I told you it could be making claims about causation. And this is why causal modeling is so important for AI, especially for explainable AI. I hope many of you consider doing a master's in explainable AI, which is I'll be happy to supervise. Well, if you do well in my course, obviously, because you need these things for that kind of thinking. But yeah, I mean, I'm happy to talk about that after the class. After the exam, if you want to go and help, if you want me to help you brainstorm topics in explainable AI, I'll be happy to do that with you. Okay, so these are the assumptions, right? Let's talk about actually learning it. So even with infinite data, we generally cannot identify the exact true causal graph from observational data alone. And what we often do get is, what we can often get from the structural learning stuff that I've shown you, we get what is called equivalence class of graphs. That is, different graph structures which give us the same set of independence assumptions. So these graphs, as I said, give us the same conditional independencies. And to pick the right one, the one that gives us the data generating process, which is the arrows in the right way, it's not identifiable. We can't pick the one that's correct. And so there are different approaches to structural learning, right? There's constraint-based methods, there's the score-based methods, there's the Bayesian model averaging, and this one is the most promising actually for this problem. The Bayesian model averaging, it gives us a very nice way to keep multiple possible causal structures in play. And what's nice about that is that it doesn't rule out certain graph structures. So if you forgot what Bayesian model averaging is, it's in the structural learning slides. It says that what we do is we average out over all possible parameters and over all possible errors given the data. So it's really a Bayesian way of looking at this problem. Of course, it's crazy difficult, but it's a good way of doing it because it doesn't rule out certain structures. It kind of like averages across structures. So instead of saying as score-based structures do or constraint-based approaches do, it says this is the graph. All right, no, that's not what it does. It says these are the plausible graphs with different degrees of support. That's the Bayesian philosophy. And isn't that a more honest way to reason under uncertainty? Okay, so let's look at an example. Oh, not yet. We first have to look at these equations. So interventional data is explicitly useful for learning causal models. When we intervene on a variable, we break its normal causal mechanism. So when estimating parameters, we should not use data points where that variable was directly intervened on to learn its usual conditional distribution. Right? So the formula on the slide counts occurrences only in data instances where there was no intervention at that variable being estimated. So by doing this, we learn a natural mechanism for the variable rather than artificial behavior created by the intervention. And the key idea is that the intervention data is valuable, right? It is, but you can't double count, right? So if we ignore which variables were intervened on, we may accidentally estimate the wrong mechanism. I know it sounds very complicated, but look at what's actually happening here. Here we have an example of a ordered sufficient statistic, unlike before, right? So here we're counting occurrences where X has occurred, right? But also where the parents has taken the values of U, right? But in this order, and we don't double count. Right, so the intuition here is that we count the number of occurrences in this event in the data instance where there is no intervention in xi. And then we use that as the parameter for whatever we're trying to model. Okay, sounds very complicated, but it's not. And you'll see on the next slide. Okay, so let me show you how to do that quickly. So let's look at an example of learning from the interventional data. Right, so here we've got an example of some interventional data. It was given to us. And we have X goes to Y. So this is the causal model. Now before we wouldn't care about the arrow, now we do care about the arrow. Because specifically we count evidence depending on where the evidence set comes from. In this case here, the sufficient statistic starts with this X, and then it has the parent variables for U. So, but we do not count the evidence of observational samples. Again, if we're looking at this particular sufficient statistic. So if our set, okay, let me put this a bit more bluntly. If your sample comes from where we force the sample to take, if the sample value for X comes from a place where we force the value of X to occur through intervention, then we don't count that particular sample. And that makes sense because obviously then you'll be tampering with what the value of the parameter is. All right. So let's look at what our data actually looks like. Before, we only had this in the other data samples from the previous lecture. On structure learning, we just had this, and we had like a list of samples. So here we had things like, for example, 4 times in the data, X is 1 and Y is 1. 1 time in the data, X is 1 and Y is 0. Once in the data, X is 0, Y is 1. And 4 times in the data, X is 0 and Y is 0. All right, so 10 samples, and that's all the samples, ends of story. Now we do structure learning, okay, or we do parameter estimation. Well, in causal modeling, in interventional data, we can force a variable because we know what the structure is of the causal network. We can force a variable to take on a particular value. So we force X to take X1. If we force X to take X1, then Y1 occurs twice. If we force X to take X1, then Y0 never occurs. Okay, so that's just the dynamics of the causal model. And finally, if we force Y, the variable Y, to take on the value Y1, then X takes on X1, and 50%, it could also take on X0. Okay, so this is very different kind of data from what you've seen before. We have like 3 pots of data, all for when we're forcing X and Y to take on different values. And we can force Y to take a particular value, we can force X to take a particular value. And so now we want to calculate some sufficient statistics so that we can calculate something meaningful. So we decided we're going to calculate these 6 sufficient statistics. The first one is this, the counts of x1. So we look at this table now and we say, okay, so remember what we said before, we can't count the places where we forced x1 to take on x1. Right? We're going to count x1s, but we can't choose that one, because if we choose that, then we biased it by forcing x1 to take on that particular value, x to take on that particular value. So we're going to count this one where x was 1 naturally without forcing anything and y was 1. So we'll count those. We'll count the scenario where x was 1 naturally with y 0, where we didn't force anything. We won't count the 2 where we forced x1 to take on x1, okay? But we'll count this one over here, and we'll count this one over here. So it becomes 4 plus 1 plus 1 plus 0, and so we end up with 6. For x0, similarly, we'll count this one, this one, this one, and this one, okay, which gives us 6. And now, remember, the order matters, right? These are ordered sufficient statistics. So here we're looking at, if this is x1 in this case, and this is the first thing we count, then we look at the parent of it, which is the ui. In this case, we're looking at y1, and the parent of which is x1. So just because I wrote y first, don't get confused, right? I wrote it like that because the sufficient statistic is specifically ordered in that way. It's ordered as this is the child, this is the parent. And so this has to be y1. You can't put x1 first. You have to put y1 first, so that it's ordered in that way. And then x1 is the parent, which comes after that. And for that one, we count where they occur naturally like that, which is x1, y1 here. We also count where, so that's going to be here. So we count this 4, and then we also count where we forced x1, right? We don't count where we force y1. We count where we force x1, and so that is over here twice. So that's 4 plus 2. Okay. Similarly, we count y0 and x1, which is this one over here. Okay. Where they occur naturally and where we forced the parent to take on x1. So that's 1 plus 0 here. Then y1 x0 in this scenario here, where they occur naturally and where we force, where the parent was forced to take on x0. And again, the last scenario is y0 x0, which is this one over here, where they occur naturally, which is the 4, and where we force the parent to take on x0, which is not the scenario here, so it becomes 4 plus 0. Okay, so this is basically the idea behind it. They're all following this formula, right? Just counting by keeping track of what's going on in the evidence. Okay, so once we calculate the sufficient statistics, we are at the final step of this very difficult lecture on causal reasoning, but I hope you enjoyed it. There's a lot to appreciate in causal reasoning. And this is to calculate the parameters, right? So remember, we calculate the sufficient statistics specifically because we want to calculate the parameters. And so to calculate this parameter, all you would need to do is say, well, what is this number? It's going to be 6, and you can divide it by adding up all of these numbers. So that becomes 4 plus 2, which is 6, 7, 8, 9, 10, 11, 12. So 6 divided by 12 is 50%, which is 0.5. And then we also have this one, which is the parameter y1 given x1, y1 given x1, which will be this number divided by the sum over the variable in question, all possible hypotheses, which is going to be this one and this one. So it becomes 4 plus 2, which is 6 divided by 7, because it'll be 4 plus 2 plus 1, which is this as the numerator, and this plus this as the denominator. So what is that? 6 divided by 7 is 0.857. Yeah, there we go, 0.86, so it's correct. And the same way, We calculate this one, which is the sufficient statistics for y1 x0, which is this here, okay, which is a 1 divided by the sum for y1 x0 and y0 x0. So this is the numerator, and this plus this is the denominator. So that becomes 1 divided by 4 plus 1 is 5. 1 divided by 5 is indeed 0.2. There it is. Okay, so that's how you would do something like this. You can calculate the different parameters using interventional data. Okay, so, oh, wow, what a lecture, hey? So much to learn. There's so much to talk about. Okay, so let's summarize this lecture by saying that graphical models is really cool, and we extended a language that we spent so much of time on, this graphical model stuff, into causal graphical models. We look how much we inherited. We took all of the Bayesian inference. We took everything, the structure learning. This lecture is so exciting because it brings everything together in a completely different interpretation. So now we now surpass statistical associations into causation. And it gives us a framework to think about causality. It gives us a framework to compute interventions, to compute counterfactual queries. Okay, we also spoke about, I think I remember we spoke about why correlation does not imply causation. And we said that is because of things like confounding variables, selection bias, noisy data, if I can remember, it's mostly misleading associations. We then also spoke about things like we can simplify causal queries into observational queries if they are identifiable, and I showed you cases of when they are identifiable or not. Then we looked at the functional causal models, which is a very fine-grained way of looking at the model mechanisms. And with this, we were able to answer counterfactual questions, like in the example of the random control trial. And yeah, so I think that's what I really wanted to teach you. Yeah, so the big message here is that of this lecture, more like this course, right, is that you have all of these different ways of representing things. And I think that the biggest message that I want to give you as your lecturer for graphical models is that this framework is so powerful because it's so modular. We spoke about different representations, but what I taught you today in causation, you can apply to any of the representations I've taught you. For example, you can have a causal hidden Markov model, right? And what would you have to change? Not much, right? You would inherit all of this causal stuff that we just spoke about today into the structure of a hidden Markov model. And then maybe talk about or argue about what does the observation model look like? What does the transition model look like? Okay, and what is the new interpretation of this? And how do you then answer an intervention query in a hidden Markov model? All right, so do you see, just by learning a little bit more in today's lecture, it had a ripple effect to everything we spoke about so far. And no matter how difficult causal modeling is, it is difficult, but you can understand it if you put your mind to it. And if you're good at this stuff, like I told you, if you're good at graphical models, if you feel like you want to learn more about it, yeah, we'll find a topic for you in uncertainty, and yeah, we'll aim for the masters, which was really the reason why I started this course in the first place. I felt like lots of students are missing out on this really cool research avenue that makes them very valuable, and it'll be a shame for our VIT students who are really the best. I mean, there's no doubt about it. Who are missing out on all of this. They could do research. And so one of my students, Tamlin Love, for example, he didn't do my course, but I supervised his honors and his masters. And a lot of it was on graphical models. And we had lots of conversations about it. And now he's gone on for a very successful career in Barcelona, in Spain. He joined a research institute there, and he's doing really well. And he now works in causal graphical models. So yeah, so all I want to say is that this is an exciting avenue. It's the state of the art. Sure, it's difficult, but nothing worth, yeah. So there's nothing that matters that doesn't come with a bit of effort. All right. Thank you, everyone. Have a lovely evening. Bye.